boiler buckling today. So here's our column. We've got a load P on it, and the deflection is Q. If we plot load P against deflection Q, if we could make a perfect column, which of course we can't, if we made a perfect column, we'd have this red stable path, which would become unstable at a certain critical load, and there'd be a point of bifurcation, and the deflected path would come out and it would be stable. So this is an example of symmetry breaking. And this is an example of what we've got a pitchfork. So if you think about it, it looks, the red shape looks a little bit like a pitchfork. If you imagine the column were imperfect, in other words, if the column were a little bit bent to the left originally, and you tested that imperfect column, it would have a propensity to go this way, and you wouldn't hit the point of bifurcation. And that's going to be an important point that I'd like to explain in a few minutes. Okay, you can think again about, you can draw energy surfaces, just as I was showing that you can think of a ball rolling on a surface and the surface gradually changes. You have the same thing here for the pitchfork. There are two types of pitchfork. This one, which was the column that we've just seen, is a supercritical pitchfork. You get a stable path coming up and then a second path which is stable. And notice the ball has been sort of pushed out of the center by a little rise in the energy surface that it's rolling on. This is a subcritical pitchfork, which is a bit more dangerous because if you come up to here, the ball now finds itself on a hilltop and just rolls off a long way. So we could say that this is a safe version of the pitchfork bifurcation, and this is a rather dangerous form. The column we've just seen was the safe form. Nothing much happens. I mean, actually, it's bad enough for an engineer if his column buckles because deflections get very big and the material starts to fail. But this is a relatively safe bifurcation. I'm going to show you an example now of a dangerous pitchfork. Yeah. I think I'll do this one myself. Call on somebody later. This is a circular ring, which may be a little bit difficult to see, and it has to be sort of anchored down a little bit just to make sure it doesn't misbehave itself. Okay, this is a ring of wire like this, and we're going to twist it. We're going to put in some twist, and we'll see what happens as we twist it, okay? So we're going to put in some twist into the wire. And because it's a dangerous bifurcation, we expect things to happen fairly suddenly. Quite hard work twisting this. Okay, it's jumped into a figure 8. And it jumped suddenly. It didn't sort of hang around. It was a dynamic jump. It went to a new solution. If I unload, nothing happens for a little while. It stays where it is. Then it gives one little flick out. And then if I unload further, another flick out. And of course, this happens in DNA, and I shall be talking about DNA a little bit later. So that's an example of a dangerous bifurcation where you get a sudden jump. Okay, so here's the big challenge question. How is this going to float? This is, as I explained before, this is a bit of maple wood. Its density is 0.78 relative to water. It's clear from symmetry that it can float as a square like this. I'll call that 0 degrees floating. It can float as a diamond, 45 degrees. Or it could, in fact, float as a tower. I mean, from the point of view of equilibrium, all these are obviously possible from symmetry. Okay? But, of course, they may or may not be stable. We don't know which ones are stable. So, who's going to try for the prize? How is this going to float? Who thinks it'll float as a square? Put your hands up. Anybody who thinks it's going to float as a square? What about a diamond? What about like this? What about any other way? Yeah.
I wasn't sure if it would spin.
Pardon?
I wasn't sure if it would spin.
You want if it would spin?
I wasn't sure if it would spin because you say there's no, with the ball earlier, there's no point of perfect stop.
Yes.
It's an unstable thing, so it might just spin around.
Right. I'll dwell on that. Any other suggestions? Oh well. Yeah. Sorry.
Oscillate between
Oscillate, right? Last chance, going, gone. Okay, that's my £5 safe. Well, there are two here, look, they're floating as diamonds, but that's because they've got a different density. That's a pine. I was very lucky that somebody in our road happens to have a friend who works in a wood factory and was able to supply me with all these. Maple, 15 degrees. You can come up and check later. I've got a photograph. There you are. So, why 15 degrees, you might well ask? Well, I have been talking about symmetry-breaking bifurcations, and that's exactly what's happened here. We've had a symmetry-breaking bifurcation. This is the behavior of the log. Imagine a log with a variable density. You can imagine perhaps that we have lots of different logs, or the same log can somehow mysteriously change its density. As the density increases, first of all, it's stable floating like a square, and then we get a pitchfork bifurcation, which breaks the symmetry. And it's a supercritical pitchfork bifurcation, and it gradually rolls over to 45 degrees, and then there's another pitchfork bifurcation. And then for a while it stays as a diamond, and then there's another pitchfork bifurcation, it gradually rolls back again, and then it goes up as a square again. And maple happens to be there. So it's gone through a symmetry-breaking pitchfork bifurcation, and it's now floating at 15 degrees. That just shows how important bifurcations are. You see, the idea of breaking symmetry means that you really can't guess what this is going to do because it's a symmetric object. You know, this explains why I had such trouble as a kid. I mean, when I was a kid, I used to make boats, you know, and I'd make a really super symmetric boat, you know, and I'd put a little mast on it, and I'd put it in the water, and it'd go, and I thought, well, that's funny, because I've really done this very carefully. So now I know why it was. So you should come and have a look at this later. I've got all these different density woods, actually, but maple is the only one that lies in that critical range. It's obvious that a very light one is going to float like this. For example, if you put a log on Mercury, it would be as near as damn it sitting on the table, and so it's certainly going to be square. Okay. I want to talk a little. Why I got interested in logs was that I had a grant from the Royal Navy for many years to look at the instability of frigates, and they were concerned about their frigates capsizing. A boat is very vulnerable to capsize if waves are coming from the side. And normally, if the frigate's going this way, waves are coming from the side, you normally change course because it's not a good thing to stay like that. But these frigates were pulling sonar devices listening for Russian submarines, and they can't just suddenly change course, so they have to just keep going. And they were rolling through enormous angles, and the Navy was really quite worried about that. Okay, this is some simulations done by W.S. Atkins of the capsize of a little fishing boat, just to show the sort of thing that engineers do all the time. I'm going to go on to here just to show you a typical sea state, because as John Barrow was saying, when you sit down with your theory, you sometimes begin to think that waves are sinusoidal, and you make simplifications which are really not appropriate. I wonder why this is. Oh, there we go. So this is just to remind you really how wild the sea can be, and it's particularly fishing boats that tend to capsize. Capsize is largely a problem of small boats. Very impressive how they just sort of disappear out of sight. Okay, let's get rid of that one if we can. Oh, there we go. I've gone too far forward now. Okay, so we'll have a look at the tests my research students did on a frigate, actually. We had a model frigate in the big naval test basin down at Gosport near Portsmouth, and we'll have a look at that. You get to play with really big models if you do this sort of thing. I want to go fast forward actually to about here. Okay, so there's a big boy's boat. I'm just putting some weights on to get the to correctly represent the a real frigate, and it's in this very long wave tank that they have down there, and paddles at one end send waves down the testing waves. This is my research student Ben Cotton, who worked with me for to get his doctor's degree, and this is another assistant. So here's this lovely big frigate. When boats are in waves, you shouldn't think of little waves as sort of splashing against the side. They're very long wavelength waves, and they just sort of gradually tilt the boat like this. So there's a frigate in waves, and the crockery in the dining area would not be in a very good state under those conditions. And finally, just to show how a ship does capsize, this is again a model test, of course. I don't have a real ship capsizing it. I do have a picture of a real ship capsizing, a fishing boat, but it's really in the distance. It was coming into harbour in Iceland. So this is a test done in Hamburg on a tanker in a following sea. A following sea is quite dangerous for a ship where the wave is travelling at more or less the same speed as the ship. And of course these are real conditions. These are the sort of waves that sort of tanker would experience, well, under storm conditions, shall we say. And there we go. Of course, I've just said that beam seas were bad. Well, following seas are even worse. Here's another test. I'm not going to run that for too long, otherwise I'm going to use up all my time. Seeing how I'm getting on time-wise. 5:25, yes. Pretty good.